Okay, now that we have seen all the properties of order on the set of real numbers that we developed in this section 5.4, it's now time for us to look at the exercises. So this is the first one. Here we have been asked to prove proposition 544. Let's quickly recall what the statement of this proposition says. It says that, say we have a real number x, then exactly one of the three statements is true. X is 0, x is positive, and x is negative. What it means is that we have to show that at least one, for a given x, at least one of these statements is true, and additionally no two of these statements are simultaneously true for a given x. That's what we mean when we say exactly one of these statements is true. I may have mixed up the order. A may not be this, B may not be this, but you get the point. We don't really need to know in the solution what specifically A is. We just know that these are three statements we have to prove appears for a given x and is a unique one for the given x. So that is one part. That is the first part of this proposition. The second part asks us this: if x is negative, x is a negative real number, then this implies minus x is positive, and the converse is also true, that is x is negative if and only if minus x is positive. And in the third part we have two positive real numbers x and y. We have to prove that x plus y is also positive, and I think we also have to prove that xy is positive. So we will handle this one by one. So let us first show this part. Let's start the solution. We shall first show that no two of the statements A, B and C can be simultaneously true. And the strategy for this solution, this part of the solution you can almost guess. It will be by contradiction. We will suppose that say A and B are simultaneously happening, then we will arrive at a contradiction, then with B and C and so on. Okay, so suppose x, which is already given in the statement, I mean the original statement of proposition 544. Suppose x is both positive and negative, then by the definition of positivity and negativity of a real number, x is the formal limit of an, and at the same time x is the formal limit of bn, where AN and BN are Cauchy sequences of rational numbers such that AN is positively bounded away from 0 and Bn is negatively bounded away from 0. Okay, so this much are the consequences of X being both positive and negative. Now, what does it mean for AN to be positively bounded away from 0? Namely, that there is a positive rational number such that AN is greater than or equal to that rational number for all the indices n, and similarly one for Bn, which is negatively bounded away from 0. Then there exist rationals C1 greater than 0 and C2 less than 0 such that AN is greater than or equal to C1 and Bn is less than or equal to C2 for all n greater than or equal to 1. Okay. Now AN minus Bn. Now look at this distance between AN and Bn. Since AN is greater than or equal to C1 and C1 is positive, for all n, AN is a positive rational number. Like that, Bn is less than or equal to C2 and C2 is negative, so all the Bn's are negative. That means all the minus Bn's are positive. So it's a sum of two positive rational numbers. I mean, inside the modulus, AN minus Bn is a sum of two positive rational numbers, AN and minus Bn. So from properties of rational numbers, the sum will itself be positive, and that's why from the definition of the absolute value function, this is equal to AN minus Bn. Now AN is greater than or equal to C1 and Bn is less than or equal to C2, so minus Bn will be greater than or equal to minus C2. Now since C2 is a negative rational number, minus C2 is positive, so that means we are actually adding a positive rational number minus C2 to the rational number C1. That means this will be strictly greater than C1 because minus C2 is positive for all indices n greater than or equal to 1. This shows that the sequences AN and Bn are not eventually C1 close, because all the possible differences that we are considering between the corresponding terms of an and bn, they are all strictly greater than C1. So you cannot go far enough down the sequence and get these distances between the corresponding terms of an and bn less than or equal to C1. That is never going to happen. So that's why these two sequences are not eventually C1 close. This and this are not eventually C1 close. Note that the term C1 close makes sense. Although this is not C1 close, but the term itself makes sense because C1 is a positive rational number. Hence, the sequences an and bn are not equivalent. Which contradicts these equations. Because the formal limits of two sequences are equivalent, equal if and only if the sequences are equivalent by definition. So this is contradicted. Thus, our supposition is, okay, power has come back, is wrong. That is, x cannot be simultaneously positive and negative. Next, we make a similar supposition and proceed accordingly to show that that supposition is also wrong. Next, suppose x is equal to 0 and x is positive. Okay, so being positive, x will be the formal limit of a Cauchy sequence of rational numbers that is positively bounded away from 0. Since x is positive, x is equal to the formal limit of an prime where an prime is a Cauchy sequence of rational numbers that is positively bounded away from 0. Thus, there exists a rational C greater than 0 such that an prime is greater than or equal to C for all n greater than or equal to 1. This implies the distance between an prime and 0. Since each an prime is positive, that's because each an prime is at least C and C is positive. So this absolute value is equal to an prime, which is greater than or equal to C, which in turn is strictly greater than C by 2 for all n greater than or equal to 1. Thus, an prime and the constant sequence 0 or the 0 sequence are not eventually C by 2 close. Hence, an prime and the 0 sequence are not equivalent. Contradicting this, that x is the formal limit of an prime and at the same time x is the formal limit of the constant Cauchy sequence, all of whose terms are equal to 0. This is this second equation is coming from our assumption that x is, where is it? X is equal to 0. In fact, if you want, you can write one more line, one more step. So our last supposition is wrong, that is, x cannot be simultaneously 0 and positive. And there is only one more case left, that we have to show that x cannot be simultaneously 0 and negative, which however can be approached much like this second part. So we just simply mention one can similarly prove that x cannot be simultaneously 0 and negative. So what we endeavored to show in this part of the solution we have achieved. Thus, not more than one of the statements are simultaneously true. Okay, are simultaneously true. We now come to the portion of the solution where we now have to show that at least one of these three statements must be true. Next, we show that at least one of the statements A, B and C is true for a given x. If x is 0, then certainly one of these statements is true, which is x is 0. So we start by assuming that x is non-zero, and then we will try to show that x will then either be positive or negative, and that will get the job done. Assume that x is non-zero. Now x is a non-zero real number. So from a previous lemma which we needed when we were encountering difficulty while defining the reciprocal of a non-zero real number, it's that lemma which says that if a real number is non-zero, then it is the formal limit of a Cauchy sequence of rational numbers that is bounded away from 0, not positively or negatively, just bounded away from 0. Then there exists a Cauchy sequence, say Cn of rational numbers that is bounded away from 0 and we can write 0 in symbol also. It means the same thing. Whether you write 0 as a word or using a symbol, it means the same thing. Okay, so that is bounded away from 0 and x is the formal limit of that sequence. Since Cn is bounded away from 0. So now we are going to use the definition of bounded away from 0. There exists a rational k greater than 0 such that the absolute value of Cn is let me continue from there. If I seem a little less energetic than usual, it's because I'm not feeling quite well, but I am not feeling so unwell that these things cannot be done. So that's why I'm slowly doing it. Why stall if we can go forward somehow, such that absolute value of Cn is greater than or equal to k for all indices n. Okay. Now if it happens that this sequence Cn is, besides being bounded away from 0, is actually positively bounded away from 0, then by definition x is positive and we have nothing else to show. We have shown that one of the conditions B and C is true, that based on the assumption that x is non-zero, x is positive. And on the other hand, if this sequence Cn turns out to be negatively bounded away from 0, then also by definition x is negative. So in that case also we are done. So let's just mention that if Cn is positively bounded away from 0, then x is positive by definition of positivity. If Cn is negatively bounded away from 0, then x is negative. Okay. So we now assume that none of these things is true. Assume that Cn is neither positively bounded away from 0 nor negatively bounded away from 0. Okay, now in this situation what should we do? We should first feed this some ink and then only other things will come. Then the sets S1, we are considering now two sets. S1 is the set of all positive natural numbers such that Cn is less than or equal to minus k, and S2 is the set of Cn is less than or equal to minus k and Cn is greater than or equal to k. Is that what we are doing? Let me see. I can't quite get what we have done here. Then or equal to minus c, or yeah, okay. And S2 is the set of those positive natural numbers corresponding to which the terms Cn are all greater than or equal to k. We are saying that because of this assumption, both these sets are non-empty. Why? Let's look at these inequalities. Absolute value of Cn is greater than or equal to k. Any such inequality is equivalent to two inequalities. Either Cn is greater than or equal to k, or Cn is less than or equal to minus k. We already know these things, and this is true for all n greater than or equal to 1. So that means if we consider any positive integer n, for that either this is true or this is true, because that we are getting from this condition. If you arbitrarily choose any positive integer n, either this is true or this is true. Now what about non-emptiness of these sets? Say S1 is empty. Suppose S1 is empty. That means for every positive integer n, Cn is not less than or equal to minus k. But one of these things has to be true. That means for that positive integer n, Cn has to be greater than or equal to k. Now if we are assuming that S1 is empty, that means no positive integer belongs to S1 because it is empty. That means all the positive integers must belong to S2. That is because you can see from the definitions of S1 and S2 and from these inequalities that the set of positive integers is actually equal to S1 union S2, and that is because for a positive integer either this is true, in which case that n will belong to S2, or this is true, in which case that n will belong to S1. Okay, so the positive integers, that set is the union of S1 and S2. So if S1 is empty, then this is equal to S2. That means for every positive integer n, Cn is greater than or equal to k. Now, since k is a positive rational number, what will that condition tell us? It will tell us that the sequence Cn is positively bounded away from 0 because all of its terms happen to be greater than or equal to a positive rational number. And because x is the formal limit of Cn, this would then tell us that x is positive. On the other hand, if S2 is empty, then the set of positive integers becomes equal to S1. That means for every positive integer n, this is true. And this in turn tells us that the sequence Cn is negatively bounded away from 0, which, if you combine with this thing, tells us that x is negative. But we have already assumed that Cn is neither positively bounded away from 0 nor negatively bounded away from 0. So neither S1 nor S2 can be empty. If S1 is empty, then Cn is positively bounded away from 0. If S2 is empty, Cn is negatively bounded away from 0. So because of our assumption, these two are non-empty sets. Let me just keep this part. It's not a part of the solution, but it elaborates the situation. So these are non-empty sets. Now next we claim that both S1 and S2 cannot be infinite. Let's see. Next, we claim that both S1 and S2 cannot be infinite. Contrary to this, let's suppose that S1 and S2 are both infinite. We are now going to use the fact that after all, Cn, whatever sequence it may be, it's a Cauchy sequence. Okay. Since Cn is Cauchy, exactly what is it that we have done here? How have we used the condition of Cauchiness? Oh, since Cn is Cauchy, there exists a positive integer n such that the absolute value of Cn minus Cm is less than or equal to k, where k is that positive integer which arose from the fact that Cn is a Cauchy sequence that is bounded away from 0. Okay, which I wrapped off. It was here. K is positive. K is a positive rational number. For all n and m greater than or equal to n. Now look at our supposition. S1 and S2 are both infinite. So that means no matter how large this capital N is, we can always find an integer, a natural number, a positive natural number in S1 that is greater than n, simply because S1 is infinite. So capital N cannot possibly be greater than all the elements of S1. That is coming from the infinitude of S1. And similarly, because S2 is also infinite, we can choose an element from S2 that is greater than n. Since S1 and S2 are infinite, we can choose, say, what shall we choose? N prime in which one? N prime in S2, N prime in S2, and M prime in S1, such that they are both greater than or equal to n. Now we calculate this thing, Cn prime minus Cm prime. One thing is that, I should have written k first. K is greater than or equal to Cn prime minus Cm prime. Okay. Now n prime is coming from S2. So Cn prime is greater than or equal to k. In particular, since k is positive, Cn prime is also positive. So Cn prime is positive. M prime is coming from S1. So Cm prime is less than or equal to minus k. Since k is positive, minus k is negative, so Cm prime, not minus Cm prime, okay, Cm prime alone is negative. So minus Cm prime is positive, so it says sum of two positive rational numbers, Cn prime and minus Cm prime. So this will be positive, and that's why this absolute value is equal to Cn prime minus Cm prime. Okay. Now Cn prime is greater than or equal to k, and Cm prime, yes, M prime belongs to S1, so Cm prime is less than or equal to minus k, or minus Cm prime is greater than or equal to k. So this is also greater than or equal to k, that is equal to 2k, which gives us the absurd inequality if you cancel k from both sides, which you can do because k is a positive rational number, but doing so you get this. Note that k is positive. So that means our supposition that both S1 and S2 are infinite is wrong. It has to be wrong. Must be wrong. So at least one of them has to be finite. Oh, I should not say at least one of them has to be finite, because we have already seen that the set of all positive integers is the union S1 union S2. Now that we have proved that both of them cannot be infinite, so one of them has to be finite and the other has to be infinite, because otherwise if both of them are finite, the union will be finite, proving that this set is finite, which it is not. So that's why now one of them will be finite and the other will be infinite. If S1 is finite, then it has a largest element M, say. Now consider the sequence Cn. Now n, instead of varying from 1, we are making it vary from m plus 1. Clearly this sequence is eventually this sequence is equivalent to the original sequence Cn. Why? Because starting from this stage m plus 1, the sequence is identical to the sequence Cn. That is, it's like this. The original sequence Cn looks like this. And so on. And our sequence, this new sequence, it starts from Cm plus 1. Okay, so these two sequences are clearly equivalent, and hence the formal limit of this sequence is also equal to x. Since the sequences this and these are equivalent, we have x equal to, we cannot write it this way, because in this notation where you write x as the formal limit of a sequence, where the sequence starts from, that is not a part of the notation, so we have to write inwards. We have x as the formal limit of this sequence also. Okay, now note the fact that M was the largest element of S1. So that's why all the indices in this sequence, M plus 1, M plus 2, etc., all of them will belong to S2, and according to our definition of S2, let's just write S2 for a moment here. N is greater than or equal to 1 and Cn is greater than or equal to K. Okay, so this was S2. So that just tells us what? Because all these indices belong to S2, so the corresponding terms Cn all will be greater than or equal to K, where K is a positive rational number. That means although the original sequence Cn was not, we did not know whether it is positively or negatively bounded away from 0, but here we know that this sequence is positively bounded away from 0. Moreover, this is positively bounded away from 0, since M plus 1, M plus 2, etc., these all belong to S2. Thus, X is positive. We have now finally been able to conclude that X is positive. So this is the case when S1 is finite. If S2 is finite, one can similarly show that X is negative. So this proves that if a real number is non-zero, then it is either positive or negative. That means the statements A, B and C, at least one of which is true for a given real number X. Okay, now we go to the next part, which tells us to show that X is negative if and only if minus X is positive. Assume X is negative, then X is the formal limit of some sequence Dn, where Dn is a Cauchy sequence of rational numbers, that is negatively bounded away from 0. So there exists a rational d greater than 0 such that dn is less than or equal to minus d for all indices n greater than or equal to 1. Then minus dn is a Cauchy sequence. We already know that if we multiply all the terms of a Cauchy sequence by minus 1, of a Cauchy sequence of rational numbers by minus 1, then the resultant is also a Cauchy sequence. In fact, that ensures that the operation of negation of real numbers is well defined. Okay, so then this is a Cauchy sequence such that minus dn, from these inequalities it follows that minus dn is greater than or equal to d, which is greater than 0 for all n greater than or equal to 1. That is minus dn is positively bounded away from 0. Now by definition of negation of a real number, minus x is minus 1 times x. That's how we define negation. Minus 1 is the formal limit of the sequence of rational numbers, all of whose terms are equal to minus 1. And x, of course, for x we have a formal we have this formal limit. So this is limit of dn. Now if we apply the definition of the product of two real numbers, we get this equal to the formal limit of minus dn. That means minus x is the formal limit of the Cauchy sequence minus dn, which is positively bounded away from 0. Thus, by the definition of positivity of a rational number, minus x is positive. Hence, minus x is positive. The converse, which says that if minus x is positive then x is negative, can be similarly proved. Similarly proved means you can try it as an exercise, as a homework problem. Converse can be similarly proved. So in the converse, it will be given to us that minus x is positive. So you will start by writing minus x as the formal limit of a some sequence of rational numbers that is positively bounded away from 0, and then you have to conclude what can you say about x. The rest of proposition 544, namely the statements that if x and y are two positive real numbers, then x plus y and xy are also positive, that part are easy consequences of this definition. Five, 4, 3. This is the definition which defines what positivity and negativity of real numbers. So here the solution ends, the proof to this proposition ends. Let's now see, we will solve 3 more exercises. Prove the remaining claims in proposition 547. In the text we proved only one part, now we have to prove the other parts, and we are going to again one by one recall what the parts are. Part A, before we write these things, let's mention, in what follows x, y and z are real numbers. So part A asks us to show that the order relation on the real numbers satisfies trichotomy, that if x and y are two real numbers, then either x is greater than y, or x is less than y, or x is equal to y, and no two of these three things can occur simultaneously. So we can in fact give the names also. The statements x equal to y, x less than y, and x greater than y are respectively equivalent to x minus y being 0, x minus y being negative, and x minus y being positive. And in fact, the definitions of these relations are just this. Okay, when x minus y is negative, we say that x is less than x. By proposition 544, which we have proved just now. Exactly one of the following three statements is true, that x minus y is 0, x minus y is negative, and x minus y is positive. Every real number is either 0 or negative or positive. So correspondingly, exactly one of the following three statements is true. X is equal to y, x is less than y, x is greater than y. So this just simply proves that the order relation satisfies trichotomy. There is something else written here. Do we really need? Let's just mention, note that definition 546 implies that x is greater than 0 if and only if x is positive and x is less than 0 if and only if x is negative. Okay, so this is part A. Then in part B, order is antisymmetric. So for that we assume that x is less than or equal to y and also y is less than or equal to x. This means either x is equal to y or x is less than y, and either y is equal to x or y is less than x. Our aim is to prove that x and y are the same, that is x is equal to y. Suppose to the contrary that they are not equal, then this since this must be true and this must be true, so in each one of these statements this part is not true. That means the other thing has to be true. X is not equal to y, so x has to be less than y and y has to be less than x. Then x is less than y and y is less than x. Which contradicts part A, where we have proved that no two of these things can simultaneously be true. Thus, our supposition is wrong and we must have x equal to y. So this is antisymmetry. Then order is transitive. For that we let x be less than y and y be less than z. Then y minus x, by the definition of order, y minus x is a positive real number and so is z minus y. Now if we add two positive real numbers, we get a positive real number by proposition 544 proved in the previous exercise. Then by proposition 544, zero is also less than y minus x plus z minus y, which is equal to z minus x. Thus x is less than z. This is transitivity. And finally, addition preserves order. Let x be less than y. Then y minus x is greater than 0, since y minus x can be written as y minus z plus minus y plus z minus x plus z. We have y plus z minus x plus z. This implies x plus z is less than y plus z. So that just shows that addition preserves order. So this completes the proof of this proposition. Proposition 547, which itself is just like proposition 429, which deals with these things where the components are rational numbers. Proposition 547 extends that all the statements to real numbers. Then exercise 543. Show that for every real number x, every real number x, there is exactly one integer n such that n is less than or equal to x and x itself is less than n plus 1. I recall a similar result that we proved in proposition 441, I think, but that was about rational numbers and this is about real numbers. This fact gives rise to the object known as the greatest integer function or float function. We will see more about that later. Okay. This integer n is called the integer excuse me, part of the real number x and is sometimes denoted by this symbol. We will start with the real number x, of course. We will then, because x is a real number, it will be the formal limit of some Cauchy sequence. From the boundedness of that Cauchy sequence, we will try to proceed, because we already know that every Cauchy sequence of rational numbers is bounded. We have proved that. Let x equal to limit an where an is a Cauchy sequence of rational numbers. Since we are not saying that x is non-zero or positive or negative, the Cauchy sequence need not be of any special kind. It need not be bounded away from zero. Those things are not present here. It's just simply a Cauchy sequence of rational numbers and that's all. Since an is bounded, since an, or we can write like this, since an is Cauchy, it is bounded. So there exists a rational number c greater than 0 such that absolute value of an is less than or equal to c for all indices n greater than or equal to 1. That is, minus c, or do we now this is not necessary. Now we take the help of proposition 441. One of those parts says that for any rational number c, we can find a positive integer n that exceeds the rational number, that is greater than c. Now by proposition, did I say rational number? Proposition 441 says that for any rational number there is a positive integer that exceeds the rational number. 441 there exists a positive integer m such that c is less than m. Note carefully that this is true only for a rational number, because in chapter 4 we studied only the system of rational numbers. Proposition 441 does not apply to real numbers, it's about rational numbers. So on this rational number c we can apply one part of it. Then so now c is less than m and absolute value of am is less than or equal to c. So this is less than m. In fact, we can take inequality also, I mean the less than or equal to. Do we need that? Let's just write, be more general and write less than or equal to. For all n greater than or equal to n. That is, if we write this inequality slightly differently, then we will have this. Now this is a place where we can apply one of the results that we proved for Cauchy sequences of rational numbers. Namely that if we have, say, two Cauchy sequences an and bn of rational numbers whose corresponding terms are in a relation like this, then the formal limits of these sequences also satisfy that relation. This result we are now going to use to this, apply to these inequalities. Note that an is already a Cauchy sequence. On this side we have the constant sequence minus m, etc., which is also Cauchy. On this side we have the constant sequence m, etc., that is also Cauchy. So we can apply formal limit on both sides. On the left hand side the formal limit will be equal to minus m, because this is a constant sequence. Here also the formal limit will be plus m. Inside the formal limit will be x. So that's how we will get an inequality which bounds x using two bounds, upper bound and lower bound, where the bounds are integers. Okay, so we now invoke that result by corollary 5, 4, 10. We have minus, we are directly writing the conclusion. Okay, we won't write formal limits explicitly. You know what has happened here. Okay, so x happens to be lying in between the integers minus m and m. If x is equal to m, then if it happens that x is the integer m, then m is less than or equal to x. In fact, it's equal to x. It does not hurt to write less than or equal to x. And x is strictly less than m plus 1, simply because x is m. So in this particular case, for that this x, we have in fact found an integer m such that, where is the statement, m is less than or equal to x and x is less than m plus 1. This is when x is equal to m. Now assume x is not equal to m, that is strictly less than m. X is strictly less than m. Consider, we are now going to consider a set of some integers. Consider the set A to be the set of those integers m such that m is strictly greater than x and less than or equal to this capital M. So that means the elements in A are integers that are strictly greater than x and less than or equal to m. Do you see that this A is non-empty? It is because m itself belongs to A. M is an integer and m satisfies these inequalities. So you can take capital M in place of small m. That tells us that A is a non-empty set. Not just that, A is also finite. Now how is that, how are we concluding finiteness of A? Note that any element in A which is m satisfies these inequalities. In particular, such an m, small m, will satisfy these inequalities also. Why? Because minus m in any case is less than or equal to x. So m is an integer that lies between minus m and m in this sense. And we know that integers greater than minus m and less than or equal to m are finite in number. That's why capital A is finite. Okay, there are only finitely many choices for small m that can be element of capital A. So that's why capital A is finite. And because it is finite, it will have a smallest element. It will have a largest element also, but we need the smallest. Let's write these things systematically. Consider the set. A is non-empty because M belongs to A, and A is finite because A is a subset of the set of all integers satisfying these inequalities, and this set is clearly finite. The latter set is finite. So A is non-empty and finite, so there is, first of all, non-emptiness guarantees that there is something in A, and then finiteness guarantees that there is a smallest something in A. Let N be the smallest element of A. Since N is an element of A, N will be greater than X. N will be greater than X. Let me write like this. And because N is the smallest element of A, the smaller integer N minus 1 will not be in A, and that's why N minus 1 will not be greater than X. It has to be less than or equal to X. And let me just make sure that this conclusion is actually true. If N does not belong to, N minus 1 does not belong to A, that means what? That N minus 1 is already an integer. It will not satisfy these inequalities. That is, we will not have this. The second inequality is already true actually. Why is it true? Because you see, N being the smallest element of A is after all an element of A. So N is less than or equal to M. It has to be, and we already know that N minus 1 is less than N. So this second inequality is true. So that means for this set of inequalities to fail, the first inequality has to be false, and from that we are getting this part. Okay, yeah, now it is clear. So we have got this. Thus, so there in the other case, in this case, we have got an integer M of the required form. In this case, we have got an integer N minus 1 of the required form. Form means satisfying those inequalities. Thus, in any case, there exists an integer n such that n is less than or equal to x and x is less than n plus 1. This only proves that n exists, but the exercise tells us to show that such an n is unique. For that, we will refer to the solution to exercise 441, which we came across previously. To see why n is unique, we refer to the solution to exercise 441, and this completes the current solution. We will do one short one, and then we will call it a night. Show that for any positive real number x, there exists a positive integer such that 1 by n is less than x. Which is greater than 0. This is a simple application of the Archimedean property that we have already proved. Since x and 1 are both positive real numbers, the Archimedean property gives us a positive integer n such that nx is greater than 1. Thus, x is greater than 1 over n, and 1 over n clearly is positive. So it shows that no matter how small we choose a real number x to be, keeping it positive, that is, we choose it to be very close to the real number x equal to 0 while always being to the right of x, then you can choose a positive integer so large n that its reciprocal becomes even smaller than that x. while at the same time staying positive. So with this I end the video here. You are encouraged to comment in the comment section whatever you feel. So this is me, Lucifer, from a mathematical room. Have a nice night.